Okay, thank you for the introduction. So indeed, I'll be talking about how we optimized some processes at Glanstoff. And so Glanstoff is indeed this producer of technical yarns. Um, they actually use a material which is very familiar to you. It's PET plastic, just like in the bottles that we typically use. But they produce it in such a way that at the very end of the process, they will actually spin it into a yarn. So they pull a thread basically after this very slow polymerization process. It takes up to 7 hours. And throughout these 7 hours, sensor data is collected. And so when they pull this yarn, they will spin it up to these spools, as you see in the picture, and that's the final product. And this has very high tensile strength, so it can be used to reinforce things like car tires. And so, since they installed some sensors a year ago, they now have been gathering data, but they didn't really have the data expertise in-house to do something with this. And so we were brought on board, and they had a first challenge for us, which was to time a specific maintenance operation, to time the flushes. And I'll get to that in a second, what these flushes exactly are. But then the project actually evolved into a more general target, which was to optimize the quality of the final product. And the quality being the number of times that this thread, this yarn, would break at the very end of the process. But the first target was to time a flush operation, a flush maintenance operation. And so what is this flushing operation? Well, I mentioned it's a very slow polymerization process, taking up to 7 hours. And actually the fluid will go through up to 10 reactors. And as it does that, it becomes more and more, or it gets a higher viscosity. So it gets very sticky. And in the final reactor, the material is so sticky that it can attach to the sides of the reactor tank. And then this material gets loose again, and it becomes an impurity in the fuel, and it leads to problems further down the line. And so every now and then, the process operator will decide, well, it's been a long time since we did a flush, and the quality seems to be degrading, so we will perform this operation now. But it's mostly a gut feeling. And so our first target was to actually see how we could optimize this using the data that they had. Now, interestingly, the flush operations, we had a lot of sensor data, but flushing was a manual thing, and so it wasn't like a 0 or 1 value anywhere in the data. We had to derive ourselves when possible flushes were happening. And so one thing that we could do was to look at the pressure inside the final reactor, and when that pressure went to atmospheric pressure, that possibly was a cleaning or a flushing event. And so we created a feature that would actually count the time since this flushing operation happened. And we found an interesting correlation to the pressure inside valves and filters just after this reactor tank. And this was data that they hadn't really thought of yet to use in timing these events. But now they will start using these things, because as the pressure on these filters increases, this is because these impurities start building up coming from this final tank. And so it's a very important signal that you should do this flush, and it's much better to time it that way. And so the project then evolved into actually improving the quality overall. We already kind of helped them timing the maintenance. And then the goal became to became to reduce the number of breaks that would happen in this as we spun this yarn. But the difficulty with this, as just mentioned, we had a huge amount of data, high frequency data of up to 7 hours of the whole process. And so a first thing that we had to do was to aggregate that data into time buckets. So we knew that the fluid would spend about 1 hour in each reactor. And so for that hour, we would calculate a lot of features on the time series data. But of course, what happened in the first reactor 7 hours ago would only have an effect now in the present, when the breaks are happening. And what's happening right now in the reactor will only have an effect 7 hours in the future. So to make all these features, all these sensor values from the different reactors make sense, to let them have an effect in the current situation, we did what we call time warping. So we brought the old sensor values into the present by adding the time that it would take for the fluid to get to the final spinning machine. And so that looks like this. We brought that data into the present, and then we actually had our features ready to build our model. And once this model was built, we used an XGBoost model. Once this model was built, we had two applications. The first one was, it has actually had two benefits to it. It allowed us to validate that our features that we used were correct. So we spoke with the experts, like, look at this feature. Our model says it uses 10% of its prediction from the value of this feature. And this is what the distribution of this feature looks like when the break is happening versus when no break is happening. And then they could think, okay, does that make sense? Is this something that we expect? What can we learn from this to improve our process? So that really was an interesting discussion. And then second, we also had the opportunity to actually make the model predict optimal settings to reduce the number of breaks. So what we do is we train the model on the full data set. But in this full data set, there were a number of set points that they could directly control. And so once the model was trained, we would actually change the original data. We would change the values of these set points and see what effect it had on the predictions of the model. And so this becomes an optimization problem, and we used the differential evolution algorithm to find the optimal settings of these 10 things that it was allowed to change within reasonable constraints, and then minimize the number of breaks that the model predicted. And so the prediction for the number of breaks went down by up to 35%. And so right now we have this first iteration of the model and of the set points that the model produces is being reviewed by the experts. We're awaiting the first trial of these set points in production, but as you know, things are a bit weird right now. In the future, we might also try reinforcement learning for even more optimal control, but right now the method looks sufficient. And some lessons learned. What I hope you take away is that you shouldn't underestimate feature engineering, especially for time series data. It's really a tough challenge to do it well, to build a good model. Don't reinvent the wheel. We were tempted to build our own optimization algorithm, but we eventually just used something out of the box. And communication is key. Along this project, we kind of pivoted into different directions, but we always made sure to inform the customer on what we thought was the right course, whether they agreed with it or not. That was something that we really had to discuss a lot, communicate a lot, very important. And then finally also, just visualize your results. For non-data savvy people, it's really helpful if you can visualize things clearly, like we did with the feature effects, things like that. It's a really, really important thing. So if you have interesting sensor data, make sure to contact us at Faction, and we'd be happy to listen and help. That's it from my side. Thank you.